This is the start of Chapter 17. This is Section 1 that deals with electric potential. We're going to build on to what we learned last week in Chapter 16 and continue to move forward. Talking about electric potential, it is a type of energy to add on to the other types of energy that we've learned about. And this is a potential energy associated with charge due to its position in an electric field. So when we finished up Chapter 16, we were talking about electric fields, and now we're going to talk about the energy associated with those. So an additional component to our mechanical energy equation. We already had kinetic energy and potential energy. We talked about those early in the year, gravitational potential energy. Recently we added on elastic potential energy, and then today we're going to add on electric potential energy to round out what we're going to do with mechanical energy. This potential energy, talking about electric potential energy, is associated with a charge in a uniform field. So we're going to talk about those fields. The equation that we're going to work with for electric potential energy within a uniform electric field is PE electric is negative Q E D. Remember, we use the symbol Q to talk about charge. The capital E is our electric field strength, and again we talked about how do you calculate electric field strength in the previous chapter, and then D is going to be the displacement from the reference point in the direction of the field. So make sure you add this to your list of equations.
When two charges interact, they exert an electric force upon one another. The potential energy associated with this force is called electrical potential energy. It is a form of mechanical energy that increases as the magnitude of the charges increases, and decreases as the distance between the charges increases. In a uniform electric field, the electrical potential energy of a charged object is due to its position with respect to the direction of the electric field. Displacement of the object perpendicular to the electric field does not change its electrical potential energy. Charges that are allowed to move freely will move to positions of lowest potential energy. In the device shown here, electrons exit the central sphere and move to the outer sphere. As this happens, the electrons lose electrical potential energy in exactly the same way that a falling object loses gravitational potential energy. If a person touches the outer sphere, the charge can then pass from the sphere to the ground, where it reaches an even lower potential energy. Charge naturally flows in the direction that results in the lowest electrical potential energy.
So, finishing up where she left off, talking about charges move towards lowest potential energy, this is exactly what we talked about in chemistry too. Whenever two atoms want to bond, if it can lower their potential energy, then they will bond with each other. Also, if we were to look at what she had stated within the video, she showed that you had, let me change colors, that you had your electric field here all moving in the same direction, and she showed you a point, and the point that she kept showing you was point A, which was a positive type charge moving in the direction of the electric field. Okay, you had a point B, and then also up here the yellow lines are the electric field itself. And she had pointed out to you, depending on if that charge was moving along the electric field or perpendicular to the electric field. If it was moving perpendicular, meaning up and down, then there was no change. But if it moved along the electric field, either in the direction that the electric field is or opposite the direction of the electric field, and if you had a plus or minus charge, then it would determine are you gaining or losing potential electric energy. So if we make just a short graph out of the data talking about what happens if your charge moves along the electric field. Again, if it's along in the same direction as what you see the yellow arrows, if you're dealing with a positive charge, then you are going to lose your electric potential energy along the way. But if it's a negative charge, you'll actually gain this electric potential energy. If we're dealing with moving in the opposite direction as E, so that's the opposite direction of your yellow arrows, if it's a positive charge, you will gain electric potential energy, whereas if it's a negative charge, you're going to lose this electric potential energy. So, electric potential, talking about potential differences, an electric potential equals the work that must be performed against electric forces to move a charge from a reference point to the point in question, and you divide that by the charge. So here's an equation here for electric potential. Electric potential is the capital V that you see. And then you've got your PE electric, which we've already looked at an equation to calculate your PE electric, and then divide that by Q, which is the charge that you have that's actually moving. So that's electric potential. Now we're looking at potential difference. So electric potential and potential difference are a little bit different. Notice you've actually got your delta signs now within the exact same equation we just looked at. So if you have a difference, obviously that's the work that has to be performed against the electric forces to move a charge between 2 points in question, and you divide it by the charge. So if you have 2 points in question instead of a charge and a reference point, which was electric potential on the previous slide, if you have 2 charges and 2 points, then, or a charge moving between 2 different points in question, you can find the difference there. So you have your delta.
If a positive charge is released from rest in a uniform electric field and moves a distance d, there is a change in the electrical potential energy of the charge because of its displacement. The reference point or 0 point for electrical potential energy must be chosen. Here the reference point is point A. If the charge returns to point A, its change in electrical potential energy is 0 because the displacement, delta D, is 0. Only the difference in potential energy is physically significant. The equation for the electric potential energy of a charge Q in a uniform electric field E shows the simple dependence of potential energy on Q, E, and delta D. Just as the gravitational potential energy of a mass falling through a gravitational field decreases, the electric potential energy of a positive charge moving in the direction of an electric field also decreases. Since potential difference is defined as potential energy per charge, the expression for potential difference in a uniform electric field is the potential energy divided by the charge. In this equation, displacement is taken to be in the direction of the electric field. Displacement in a direction perpendicular to the field produces no change in potential energy.
Okay. So now I want to step back just a little bit and look at the different equations that we've seen so far and show you how to combine those. So when we started off today, we looked at electric potential energy is equal to negative Q E delta D. And when they finished up with the video that we just looked at, we saw delta V equals negative E delta D. So now we're going to take the equation, the second equation that we talked about today, which was delta V equals delta PE electric over Q, and we're going to plug in what we have for PE electric into this equation. So delta V equals negative Q E delta D over Q. And you can see how your Q's will cancel out, and what you are left with here, delta V equals E delta D, along with the negative, is what you have there at the bottom. So it's trying to show you how you can get from one point to another. So we've looked at electric potential, and electric potential is your V. Potential difference is delta V, and we get to this equation that you see here, which is what we had derived through the video. Delta V is negative E, which is your electric field, and then D is the displacement. So let's work through a sample problem. It says a charge moves a distance of 2 centimeters in the direction of a uniform electric field whose magnitude is 215 newtons per coulomb. As the charge moves, its electric potential energy decreases by 6.9 times 10 to the negative 19th joules. Find the charge on the moving particle, and then find the potential difference between the two locations. So if it says find the charge, we are definitely looking for what symbol. That is going to be Q. We're looking for Q when it says find the charge, and we are also looking for potential difference, which is delta V. So both of those are going to be question marks for us. This shows you the variables that were given, delta PE electric, the distance, and don't forget distance I believe was given in centimeters, so that's got to be turned over to meters, and then your electric field was given as 215 newtons per coulomb. Set up the equation that we had given for PE electric, and we can solve for Q here since the other three variables are given. So the charge is 1.6 times 10 to the negative 19th coulombs. And that number should look very familiar to you because that is the charge of an electron. And to find the potential difference, there's the other equation that was given. Solve for delta V and you get negative 4.3 volts. Moving on. This right here says you have an electric potential at point A, and it depends on the charge at point B. I do want to back up for just 1 second, though. Look at some of these units that we have given, because on this one, whether you're talking about electric potential or potential difference, this is measured in the unit of volts, and that's where the capital V comes in. So when I'm looking at those units, and you've got delta V, and the unit is also V, that is volts. I'm looking at this unit. And when I'm looking at volts, you can tell here you've got Newton times meter over coulomb. So that is one version there. Also, a Newton meter is the same thing as a joule. So joules per coulomb would also work. And you could keep playing with these units to get different variations of it too, but I do want you to see some of the other possibilities that could lead to this. So going back to this right here, it's showing you a charge at A, a charge at B, and they are separated by some distance r. And the second bullet point tells you that there will be an electric potential that exists at some point in an electric field regardless of whether there is a charge at that point. So there is an electric potential that exists based on these two charges that are separated by some distance. The reference point for potential difference. Near a point charge is often at affinity. So if we're looking at the equation that they have here, you've got delta V is Kc over Qr. Kc is going to be Coulomb's constant. We've already worked with it, 8.99 times 10 to the negative 9th. and then your Q is the value of a point charge, and then your R is distance to the point charge. And we go back and we look at the superposition principle again. Remember that it says that you can use this principle to calculate the electric potential for a group of charges. So again, this is talking about a reference point. We're no longer comparing two different charges or charges within an electric field. It's talking about a reference point for potential difference.
According to the superposition principle, the electric potential at a point is the algebraic sum of all the individual potentials existing at that point. The strength of the charges, their polarity, and their distances from the point in the middle completely determine the electric potential at that point. This is because, in contrast to a vector quantity, electric potential is a scalar quantity and has no direction associated with it. Calculating the electric potential at a particular point is simply a matter of finding a scalar sum.
So a couple things just to highlight what she said. Number one, she said that the electric potential here, delta V, is a scalar quantity, meaning no direction is going to be associated with it, unlike when we worked in the previous chapter and we did have to break our resultant vector up into its components. We found the angle, so we did have to work with direction there. The equation that she had was delta V equals Kc times Q1 over R1 plus Q2 over R2, and this just keeps going. It depends on how many points you've actually got. So you could have a Q3 over R3, Q4 over R4, and so on. This one does have 4 different points. It shows you your Q value, which is your charge for each of those points. It shows you the distance R that it is from the reference point, that's the black dot in the middle, and how you calculated it. So let's look at all of the equations that we've talked about today, because there are quite a few. This one I've left up here. That one right there is talking about the superposition principle, and this is for find the potential difference at a reference point. So delta V, potential difference, this is at a reference point. We've also looked at the very beginning, electric potential itself. So electric potential was V, and it was equal to PE electric over Q. We also looked at potential difference. Potential difference was delta V, which is delta PE electric over Q. We combined these equations to come up with another one, and this was delta V. If you're dealing with an electric field, your potential difference is equal to the negative of your electric field times the distance that is associated with it. So several different equations based on what all we have looked at today.